Namaste, my friend, and welcome to NEET Chemistry with Typical Monk. This is Class 1, and we begin at the very beginning, the mole. Now, here is a beautiful problem to sit with for a moment. A single drop of water holds more molecules than there are stars in our entire galaxy. Atoms are impossibly small and impossibly many. So how does a chemist ever count them? When Sarah first heard this question, she laughed and said nobody could count that high in 1,000 lifetimes. And she is right, which is exactly why chemists invented something wonderful, a way to count without counting. Today, one idea at a time, we build the single most important tool in all of chemistry. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the mole itself and Avogadro's number, chemistry's own counting unit. The idea every other calculation stands on. Second, molar mass and percentage composition. How much a mole weighs and how much of a compound is which element. Third, the difference between the empirical formula and the molecular formula, the simplest ratio versus the real molecule. Fourth, stoichiometry and the limiting reagent, how to predict exactly how much product a reaction can give and which reactant runs out first. And fifth, the NEET drills, assertion and reason, mash the column, and the numericals, so that everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the problem itself. Atoms are far too small and far too many to count one by one. Even if David counted 1 billion atoms every second of his life, he would not finish a single grain of sand. So chemists do what shopkeepers do. They count in bulk. That bulk unit is the mole. And here is the heart of it. 1 mole equals 6.022 into 10 to the power 23 particles. Recall this Avogadro's number. Do not let the size frighten you. It works exactly like the word dozen. When Sarah buys a dozen bananas, she does not count 12 every time. The word dozen means 12 always. In the same way, the word mole means 6.022 into 10 to the power 23. Always. A dozen eggs, a dozen atoms, a mole of eggs, a mole of atoms. Same idea, bigger number. Now, the magic of the mole is that it connects counting to weighing. 1 mole of a substance weighs its molar mass in grams, a number that is numerically equal to its atomic or molecular mass. So 1 mole of carbon weighs 12 grams. 1 mole of water weighs 18 grams. You weigh the substance on a balance and you have secretly counted its particles. And there is one more gift. 1 mole of any gas, hydrogen, oxygen, carbon dioxide, it does not matter which, occupies 22.4 liters at standard temperature and pressure. Number, any gas, the same volume. Sit with that for a second. It is one of the most examined lines in this chapter. Look at this diagram carefully, because it is the map for every numerical in this chapter. In the middle stands the mole, like a bridge with 3 roads leading away from it. The first road connects grams to moles. If you are holding a mass, divide by the molar mass, and you arrive at moles. 36 grams of water divided by 18, 2 moles. That's simple. The second road connects moles to the number of particles. Multiply your moles by Avogadro's number, 6.022 into 10 to the power 23, and you know exactly how many atoms or molecules you hold. The third road connects moles to gas volume. Multiply your moles by 22.4 liters, and you have the volume at standard temperature and pressure. And now, the master trick, the one habit that solves this entire chapter. Whatever the question gives you, whatever it asks for, always convert to moles first. Stand on the bridge, then hop across to whichever side you need. Lisa used to jump straight from grams to molecules and kept slipping. The day she started walking through the bridge, grams to moles, moles to particles, she never got one wrong again. Now let us read the formula, the way a chemist reads it. First, percentage composition, the mass percent of each element in a compound, and you can read it straight off the formula. Take water, 18 grams per mole, of which 16 are oxygen. So water is nearly 90% oxygen by mass. The formula quietly tells you what the compound is made of. Second, the empirical formula. This is the simplest whole number ratio of atoms, not the real molecule, only its skeleton, its simplest recipe. Third, the molecular formula, the actual count of atoms in one real molecule, and it is always a whole number multiple of the empirical formula. How do we find that multiple? We call it N, and N equals the molar mass divided by the empirical formula mass. Watch it work on glucose, and this example alone can fetch you a NEET question. Glucose has the empirical formula CH2O, 1 carbon, 2 hydrogens, 1 oxygen with an empirical mass of 30. But the molar mass of glucose is 180. 180 divided by 30 is 6. So the molecular formula is 6 times the empirical C6H12O6. The skeleton multiplied by 6 becomes the real molecule. Time to solve a full NEET numerical together, slowly, the monk's way. The reaction, nitrogen plus 3 hydrogen, gives 2 ammonia. We are given 28 grams of nitrogen and 9 grams of hydrogen. How much ammonia can we make? Step 1. Write down what is given. 28 grams of nitrogen, 9 grams of hydrogen, and the balanced reaction. Nitrogen plus 3 hydrogen gives 2 ammonia. Never skip this step. Half of Lisa's early mistakes disappeared the day she started writing the given data before touching the calculation. Step 2. Cross the bridge. Convert both masses to moles. Nitrogen, 28 grams divided by a molar mass of 28, 1 mole. Hydrogen, 9 grams divided by 2, 4.5 moles. Step 3. Compare with the ratio in the equation. The equation says 1 mole of nitrogen needs 3 moles of hydrogen. We have 4.5 moles of hydrogen, more than enough. So hydrogen is in excess, and nitrogen will run out first. Nitrogen is the limiting reagent, and the limiting reagent decides everything. Step 4. Let the limiting reagent write the answer. The equation says 1 mole of nitrogen gives 2 moles of ammonia. So our 1 mole of nitrogen gives exactly 2 moles of ammonia. Step 5. Back across the bridge to grams. Ammonia's molar mass is 17. 2 moles times 17, 34 grams of ammonia. That is the full answer, and notice the path given, moles, compare, product, mass. The same 5 steps solve every limiting reagent problem NEET can ask. Now, concentration. How much solute is dissolved in how much solution? 2 cousins live here, and NEET loves to test whether you can tell them apart. The first is molarity, written with a capital M, moles of solute per liter of solution. But notice its weakness. It is built on volume, and volume expands when you heat it. Warm the solution, and the liter grows, so the molarity drops. Molarity depends on temperature. The second is molality, written with a small m, moles of solute per kilogram of solvent. And here is its quiet strength. It is built on mass, and mass never changes with heating. John once asked, why do we even need 2 units? This is why, when temperature varies, molality stands firm while molarity drifts. Third, the mole fraction. The moles of one component divided by the total moles of all components. A pure ratio, no units at all. And fourth, parts per million, for very, very dilute solutions, like a trace of a substance dissolved in a tank of water. When the amount is tiny, we count it in parts per million. Now set up straight. These 5 lines are what NEET actually asks year after year. 1. A mole is 6.022 into 10 to the power 23 particles, and the molar volume of a gas is 22.4 liters at standard temperature and pressure. Memorize both goal. They should come to you faster than your own name. 2. Molarity changes with temperature. Molality does not. This exact pair is a favorite assertion and reason question. You will meet it on the very next slide. 3. The limiting reagent is the reactant that runs out first, and it alone decides how much product forms. The excess reactant simply waits. 4. The empirical formula is not the molecular formula. Molecular equals N times empirical. Remember glucose. where n was 6. 5. Significant figures. Your final answer can never be more precise than your least precise piece of data. Precision is honesty in numbers. Let us drill the neat way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. Molality is preferred over molarity when the temperature of an experiment varies. Reason, molality is independent of temperature. Think like Sarah. Check each statement on its own, then check the connection. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. Molality is preferred precisely because temperature cannot touch it. Both true. Reason explains. Option A. Second one, assertion. 1 mole of any gas occupies 22.4 liters at standard temperature and pressure. Reason. 1 mole contains 6.022 into 10 to the power 23 particles. Both statements are true, no doubt. But pause. Does the number of particles explain the volume? No. The molar volume comes from Avogadro's law. Equal volumes of gases hold equal numbers of molecules, not from the size of the number itself. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. 2 true statements that simply stand side by side. Third one. Assertion. 16 grams of oxygen gas contains 6.022 into 10 to the power 23 molecules. Reason. The molar mass of oxygen gas is 32 grams per mole. Check the reason first. 32 grams per mole. True. Now the assertion. If a full mole weighs 32 grams, then 16 grams is only half a mole. So it holds only half of Avogadro's number of molecules. The assertion is false. The reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. Avogadro's number 6.022 into 10 to the power 23. The count hiding inside every mole. The molar volume of a gas at standard temperature and pressure 22.4 liters. Any gas, always. Molarity, moles of solid per liter of solution. Litera, so it drifts with temperature. And molality, moles of solute per kilogram of solvent. Kilogram, so temperature cannot shake it. If all 4 came to you before the reveal, the bridge is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. Molality is independent of temperature. Hold your verdict. Statement 2. The molecular formula is always the same as the empirical formula. Think of glucose before you answer. Statement 3. 1 mole of carbon-12 weighs exactly 12 grams. This is, in fact, the very definition the mole was built on. So, how many are correct? 2 statements, the first and the third. Molality truly ignores temperature, and carbon-12 truly anchors the mole at 12 grams. But the second one falls. The molecular formula is n times the empirical, and n is only sometimes 1. Glucose, with n equal to 6, is the counterexample you should carry into the exam hall. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. The limiting reagent is whichever reactant has a smaller mass. It feels so natural. Less stuff runs out first, no? David believed this for months. But here is the truth. The limiting reagent is decided by the smaller mole ratio relative to the balanced equation, never by mass alone. Remember our worked example. Hydrogen had only 9 grams against nitrogen's 28, yet nitrogen was the one that ran out. Convert to moles first, always, then compare with the equation. Myth 2. Molarity and molality are just 2 names for the same thing. 1 capital letter, 1 small, how different can they be? The truth, completely different creatures. Molarity uses liters of solution and shifts with temperature. Molality uses kilograms of solvent and does not move at all. 1 letter, 1 full NEET question. Do not let it be the one that costs you. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the bridge you built today. Question 1. How many moles are there in 36 grams of water? Think, molar mass of water is 18. 36 divided by 18, 2 moles. Question 2. How many molecules are there in half a mole? Half of Avogadro's number, T.01, I into 10 to the power 23. Question 3. What volume do 2 moles of any gas occupy at standard temperature and pressure? 2 times 22.4, 44.8 liters. Question 4. 1 mole of solute is dissolved in 2 liters of solution. What is the molarity? 1 divided by 2, 0.5 molar. And question 5. The thinker. In nitrogen plus 3 hydrogen gives 2 ammonia. You have 1 mole of nitrogen and 2 moles of hydrogen. Which one is limiting? Careful. 1 mole of nitrogen demands 3 moles of hydrogen, but you have only 2. This time, hydrogen runs out first. Hydrogen is the limiting reagent. If you quote that reversal, you have truly understood today's class. Let us gather the whole class in one slow breath. The mole is chemistry's counting unit. 1 mole is 6.022 into 10 to the power 23 particles, just as a dozen is 12. The mole bridge links mass, particles, and gas volume, and the master habit is to always go through moles first. 1 mole of any gas is 22.4 liters at standard temperature and pressure, and the molar mass in grams is exactly 1 mole on your balance. Numerical formula is the simplest ratio, and the molecular formula is N times the empirical. Glucose C612O6 with N equal to 6. The limiting reagent runs out first and sets the amount of product, and molarity depends on temperature while molality does not. And next class, we go inside the atom itself. The structure of the atom, Thomson's model, Rutherford's gold foil, Bohr's orbits, and the beautiful hydrogen spectrum. Do not miss it. And so, my friend, we have taken the first step. It may have looked like just one number and a bridge, but understand this. The mole unlocks every calculation in chemistry. Every equation you will ever balance, every concentration you will ever compute, every numerical need will ever throw at you, they all walk across the bridge you built today. Sarah, David, Lisa, and John all started exactly where you are right now with this one class. Be patient with yourself. Revise the bridge tonight once, slowly. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you inside the atom.